We're gonna be looking at this chapter, which is complex numbers, right? This one, I think this currently we'll be using the guide of, I think it's for SMTH 012, which is the same guide for SMT Build 000, right? So let me look at complex numbers this side and see this side. Let me see which chapter is this one on SMTB. Yeah, I think they're all chapter 5, right? Both of them, it's chapter 5. So currently you guys will be moving together. So as I said, from next week we'll be attending contact. We'll be back to contact, since I'll also be done writing most of my difficult modules, right? So what you're gonna be doing from the, I think from the 17th, we can start planning which days and or the times, or we can just go back to our usual times of having classes. So when we come to, let me just go to the notes, then I just give you an introductory part of this module or the topic. Let me say complex numbers, right? So we're always going to be using this slide every time we have an online class. So when we come to this, let me just call it an introduction to complex numbers. So when we come to this introduction to complex numbers, what is it that we should be able to know? So first thing that we should know is that let me say we should be able to define the following. First, we should be able to define what is an imaginary number. We should be able to know what is an imaginary number. We should be able to know, besides, let me say, imaginary part. We should be able to know the imaginary part. We should be able to know what is it when we talk about a real part. And we should be able to know what is a modulus. So once we are able to know these, and lastly, let me say the argument. We should be able to know what is an argument. So if we're able to know this, all these are coming from a branch of a complex number. So we also need to define what is a complex number. So in other words, these are going to define a complex number. So when we talk about an imaginary number, we're talking about that thing which we say it's I. You have seen it when you were doing this topic. And a complex number is written in the form of A, B, I, or A, I, B. You see, right? And when you look at A plus B, I, the imaginary part is the one that has I next to it, meaning that our imaginary part will be B, our real part will be A, and the modulus of this complex number will be, let's say this complex number is Z. The modulus of this complex number will be the modulus of Z. These ones we say modulus, you see, right? Of Z is equals, most times we call it R. We call it R where we talk about the root of A squared plus B squared. You see, right? Where we talk about the root of the A squared plus B squared. Now, when we come to the argument, we're just going to be looking at some plane. This plane has certain rules, but we should know that we have what we call a first quadrant, a second quadrant, third quadrant, fourth quadrant. And on the first quadrant, in this case, we're always going to say this is tan inverse of B over A, or the arctan. Actually, let me just say the arctan. Arctan of B over A it's going to be the same here on the fourth quadrant, and it's going to be the same formula here, but the only difference is that on the second quadrant you are going to subtract pi. You see, right? Then on the third quadrant you are going to add pi. So here we have pi 0, pi over 2, 3 pi over 2. So here's how we know these angles, right? In this plane. What you should know about the first one here, it's like it's 0 over 2. It's 0 pi over 2, which gives us 0. This one here, it's 1 pi over 2, which gives us pi over 2. This one here, it's 2 pi over 2, which just gives us a pi. Then this one will be 3 pi over 2. So this is how you must know, right? This is what you should know, how to know. Oh, you don't have to cram them, you must just know how to bring them out. You see, right? Now what we should know is that in this case there are certain cases where we're gonna be forced to use cos, sine, and so on. So it's possible for you to find all these angles without using a calculator, right? So you should know that here in the fourth quadrant cos is positive, on the second sine is negative. Now check this is sine, this is cos, then here we're going to be looking at tan, saying that tan is positive, and here they are all positive. So we'll be looking at this plane most of the times. We're gonna be drawing this plane. If we're gonna use it, we're going to use both the calculator and also computations. You said I'm gonna teach you both, because when you get to your final level you're gonna be having a part where you're not going to be using a calculator. Actually, in this topic you're going to be doing this topic. If you're going to do math in your final level, you'll do this topic as a module, right? Then when you do this topic, you must know that you're going to be moving away from a calculator part. You're going to be calculating everything. Without the calculator, you're going to be knowing how the angles work. You see, right? Now, from what must happen here is that I'm busy. Yeah, these guys are just knocking in my door. I think that they're doing it on purpose. They don't know how to play. So now let's first look at the things which I say that we're given here, right? So firstly is we need to know what is an imaginary number. So in this case, how do we define an imaginary number? An imaginary number. So these guys, they just come here, they knock, then they run away. You see, so they get overexcited sometimes. So now when we look at an imaginary number, we say that I is an imaginary number, or we can just call it a number. We can say that I is a number. We can say I is a number such that, so that's what we want to focus on. I squared will be equal to minus 1. So this is how they defined it in our guide for both SMT B0 and SMT H012, right? So they say that I is a number such that I squared is equal to minus 1. So and now let's look at the second definition that I said that we should look at is what is an imaginary part. Now remember, with the imaginary part, I'm not really going to define it, but in this case we know that the imaginary part, if we're given the complex number a plus b, our imaginary part will be b and our real part will be a. So I'm just going to include these two inside the complex number definition, right? So it means that now what we need to define is a complex number. Since already we know what is an imaginary number, we can continue to and define a complex number, right? Now with a complex number, we are going to say that this is a number which is going to be in the form of a plus bi. You say right now, it's a number of the form let's say a I don't know what happened here. Let me do this. It's a number of the form of a plus bi. Right, let me just oh, I was not here, that's why I see something happened. So we're saying that a complex number is a number of the form a is the form of a plus bi, where now we're going to define the things which I said that we're going to define. Things like what is a, what is b, and what is I. You say right. First, before we define a, b, again we're saying that a complex number is a number of the form a plus bi. We must know where a, b, this a, b will always be an element of a real number. You say right. And the I, which we know that it's I squared equals to minus 1, meaning that the I will be equals to root of -1 in this case, right? Now, since we know that a, b are taken from real numbers, we should know that a is the real part, or is called the real part. A is called the real part, and b is the imaginary part. So it is very important for us to know this definition. We say right now, when we come to a is the same thing. Let's say the complex number here. Let's say the complex number here is z is equals to a plus bi, meaning that a will be r e of z, the real part, and b will be equals to the imaginary part of z, which will be denoted like this. I'm sure we see this, right? Now, let's look at some of the examples that we can be given. Let's see. So, we have different types of things or computations that we can do, or operations which we can do with complex numbers. So, let's look at these operations, meaning that we can say we're looking at operations. We're looking at operations. Now, the operations that we can do is addition or subtraction, let me say multiplication, or division. Yeah. And then we can also conjugate. Usually this one is not really an operation, but then I want to cover it now. You see right now. Now, when we look at things like addition, subtraction, these ones are not that difficult. They are simple to deal with, right? So now let's look at this. Let's say that now we're given a tutorial, right? I think let me just check a tutorial where we can do addition and subtraction instead of doing examples, right? So let's say, let me just look for a tutorial here. Then we can do the ones of addition, subtraction, all of them actually, right? And then we'll just compute them. Yeah. And then let me see from here. Yeah, we're just gonna do this. Here they say find the conjugate of z in the following. So let's just take this. Let's just take this and this and we add them. You see, right? So let's say z is equals to, here they say z is equals to 5 plus 2i. 5 plus 2i. And then b, they say that is equals to minus 3 plus I. Minus 3 plus I, right? Z is equals to minus 3 plus I. I'll just call this one W. So the first operation we can do is to find Z minus W. If we want to find Z minus W, we know that Z is 5 plus 2i minus W is 3 minus 3 plus I. Then we first simplify the other part. Plus 3 minus I. And then we gather together the real part. The real part is 5 and 3. And then the imaginary part is 2 and 1. You see, right? And then this will be 8. And then this will just be I. You see, right? This would be the same if I'm going to add them. This will just be 5 plus 2i plus 3 plus I. Then I put them together. 5 plus 3 plus 2 plus 1, then I outside. Then this is 8 plus 3i. Now, let's say now I want to multiply them. Meaning that if I want to multiply these two, I'm going to say this is 5 plus 2i, 3 minus 3. Oh, when I was adding this was supposed to be minus, right? Yeah. And then this is minus. Then this is 2. So, minus 3 plus I. This is going to be, when we multiply this, we're going to multiply this with this, also with this one. Again, this with this, also with this one. You see, right? This is just going to be minus 15 plus 5i minus 6i plus 2i squared. You see, right? I don't even need these brackets. And then this is just going to be equal to minus 15. And then this one, I can put it somewhere here. Then I plug minus 1. You know that I squared is equal to minus 1. Then this is plus 5i minus 6i. And then I'm going to get minus 15 minus 2. Then I just gather the real part and the imaginary part together. Then this is going to be minus 17 minus I, because that is minus 1i, right? Then this is what we would get for the multiplication. Now, let's say now we look at a division. We want to find Z over W, right? This is going to be 5 plus 2i over minus 3 plus I. You're always going to focus on the one in the denominator. You see, right? So you will want to take the one in the denominator, and then from there, what you're going to be doing is you'll take this, multiply by its conjugate. Always, when you multiply by a conjugate, that's why I said that I'm going to include the conjugate here because it's going to be very important, right? When you want to find the conjugate of something, let's first find the conjugate. Let's say a conjugate. Let's say J here. The conjugate, let's say I want to find the conjugate of W. I'm just going to do this. Is minus 3 plus I. Always, when you want to find the conjugate, you're always going to negate I. So this will just be minus 3 plus I conjugate, and this is just minus 3 minus I. So this one is not important, this step in your case. Then you're always gonna negate I. Doesn't matter whether it comes first or second, you always negate I. So meaning that when I'm going to multiply, it's just going to be minus 3 minus I over minus 3 minus I. When you multiply here, you are going to have this by this, which is a minus 15 minus 5I, so it's like this, and the same for 2, right? And then minus 6I minus 2I squared all over this. Whenever you're multiplying the denominator, right, it is much simpler for you to just come and say minus 3 squared plus minus 1 squared. These ones are just going to take their constant. Their constant is minus 1, the common constant. You see, right? You can just say this. And then here you're going to get minus 15 minus 5 minus 6. So it's going to be minus 11I minus 2 minus 1, because I squared is also minus 1. You see, right? Which is all over 9 plus 1. And then we get minus 15 plus 2 minus 11I all over 10, which this is minus 13 minus 11I all over 10. Then we simplify it. You see, right? Then we get that we should always make sure we put it in the form of A plus BI. So sometimes you'll be asked, right, to find the real part of this. Maybe they say find RA Z over W. The real part of this will just be this, minus 13, meaning that you must find this first, then you write it in the form of A plus BI, then you find its real part. Then the imaginary part of Z over W just going to be minus 11 over 10. I'm sure you see this, right? Now let's see. Let me see what else that we can look at from these operations. Yeah, I think these are these operations are fine so far. Let's look at this. Let's look at the guide. Yeah. We can look at the guide. Then we'll look at this. So find the conjugate of Z. So let me show you, right? If they tell you to find the conjugate of Z, we're going to be using this formula, right? So what you're going to be doing always when they say find the conjugate, you're not just going to come and say this is 5 minus 2i. Yes, right? You won't just say that. You're going to say the answer will be like this. You first have to show us this. You say right now. Then you come and say that this is 5 minus 2i. Then this one here, the conjugate of Z is just going to be minus 3 plus I, which this will be minus 3 minus I. And this one, minus 3i, just going to be minus 3 plus 3i. Now, this one is just root of 5 I minus 3. This is going to be minus root of 5i minus 3, because we are negating I. You see, right? And the conjugate of minus 1, it's going to be minus 1, because there's no I here, so we don't change anything. So we only negate I. I'm sure we say this, right? Now, root, the solutions are going to be like this. Now, Let's look at the properties that we're going to be working with. Remember, I said that this part was not that important, but you should know that if they tell you to find the conjugate of z plus w, you must know that this can be reduced to these two. The sign here won't be affected unless if this has an I. You see, right? Now, the same thing when you're doing the conjugate of a minus in between, the sign won't be affected unless if this has I. You see, right? And then again, the conjugate of 2 multiplied will be the conjugate of each. And for division, the same thing, the conjugate of each. And if we apply a conjugate on a conjugated complex number, the conjugate is going to cancel out. It's like a double negation. You see, right? Now, we are going to be proving this. These two, we're going to prove them. Z plus Z conjugate is equal to 2 real Z. Let's prove that. So I want us to prove this. These you can be asked in a test. The first one there, property. The first property there was that Z plus this is equal to 2 of Z, right? Now, if we let Z be equal to A plus BI, we know that the conjugate of Z is A plus BI, which is A minus BI. Meaning, and we know that A is equal to the real of Z and B is equal to the imaginary of Z. Since we know this, right, what we can do now, we can say we take the left hand side. We say that if we try to prove Z plus Z conjugate, we can have here A plus BI plus here we can have A minus BI. We know that the BI's will take care of each other. We'll be left with A plus A, and this is 2A. And what is A? A is equal to the real of Z. You see, right? Then we have proven that property. Now, looking at another property, it says that Z minus Z conjugate is equal to 2 imaginary I. Let's see that. Now, we say this, that now we're trying to prove that this is Z minus Z conjugate is equal to 2 imaginary of Z I. So, if we want to do this, they say that we are going to actually, let's say this, we're going to check the left hand side, take Z minus Z conjugate, this is A plus BI minus A plus BI, we conjugate this, right? And this is going to be A plus BI minus, inside here it's A minus BI. Let's say here I wanted to do this without first showing that the conjugate is this. I was just gonna plug my A plus B in Z. Then I apply the conjugate individually. I have A plus BI minus A plus BI. And the A will take care of each other, will be left with BI plus BI. And this is just 2BI. And what is 2B? What is B? B is the imaginary of Z. Then we have this. You see, right? So it will be simple for us to prove such cases. It does happen. They can ask you to prove them. You see, right? Now, here, with C, they say that if Z is an element of a real number, then this implies that Z is equal to its conjugate. You see, right? Now, let's look at the theorem that we have. let me see, we have the factor theorem, which they say that a polynomial f of x has a factor x minus a if and only if f of a is equal to 0. And then yeah, at least this time they did include the parts where you have to solve for the roots, right? So let me see the roots. Yeah, then when we come to these ones of the roots, guys, this is something that we've been doing before. We've been doing solve for x. We know what is a quadratic formula, so these ones won't be that much of difficulty. We're gonna be able to solve them, right? So the only difference that we get in this point is that we remember before when we were using quadratic formula to solve, the moment you'd find a root of -1, this thing would not exist. But in this point, it does have some change, because we know that the root of -1 is equal to I. So this is the only difference that we can have here. And using this, we know that if you are unable to factor out, some they use the long division, some the other things, the synthetic what method, right? I forgot that one, but I only use long division because throughout you're gonna be using long division. This is the one that we're gonna be using the most. So what we're gonna be doing now for these ones, or maybe let me first check how many people do we have here before I can take a decision. Yeah, so for these ones, what we can do, right, we're gonna be doing them when we come for a contact session. These ones, the ones of long division. Long division is very simple. First thing that you do, we remember first thing we do, we're going to find actually here we're even given, they say given x plus 1 is a factor for the expression. We must they say find the other two factors. But we know that if we're not given, we should probably try to substitute so that we can find a factor that when we plug we get a 0, right? Then we're going to use it to divide. So we're gonna be doing that. So let me check the things which we're supposed to do. Operations with complex numbers, we have done this. We have done the z plus, z minus. Yeah, let me look for something we haven't done. The division, we've done it. Yeah. And then they come here and say that we should simplify the following expression and write the answer in real imaginary form. Remember when we were supposed to write the answer in real imaginary form, it means that you're supposed to come and simplify this to the form of a plus bi. Meaning that if we were going to simplify this, we're going to have I, this would just be 4, plus this is just 2 times 5 is 10, times 2 is 20, this will just be 20, I plus, then this times this is 25 squared. So let me show you, right? So what I do here, mostly for me to write this fast, right? First thing that I do, I take this squared, which is gonna be 2 squared plus, right? And then you're going to take this squared, which should just be 5i squared. And then you're going to multiply all these terms together. You put it in the middle. So it's like 2, 5i. You see, right? And this is going to be I, this is 4 plus this 10, 20 I plus 25 I squared. You see, right? This is the simplest way to do it. But if you feel like that way is difficult, what you can do, you can do it the easy way, right? Just do this 2 plus 5i, 2 plus 5i. If you're fine with that, this times this is 4 plus 10i plus 10i. It's like you multiply this, then you multiply this. Alright, then it's plus. Now, no, this one I mistakenly added this. Yeah, Then when you multiply these, right, what you're going to be having here, you're going to be having 25i squared, and this is what we have there, so which is inside. Now we're going to simplify the inside, right? Or to make it simple, we can just multiply this is 4i plus 20i squared, and remember this was going to be minus 25 because I was going to subtract minus 1 here, so this is just going to be minus 25i. So it is much better to start by simplifying the inside. So I'm sure we've seen now when we're trying to compute, so it will be much better if I come here and say that this is going to be 4 plus 20i plus 25 minus 1, which is also I4 minus 25 plus 20i also I plus 21 plus 20i. Then here I was going to get minus 21i plus 20i squared. And already, if it's minus 21i plus 20i squared, this is minus 1. I squared, we know it's equal to minus 1, then you're going to get minus 21i. You see, right? If you just plug minus 1 there. Now, we look at b. B, it is much better if you start by simplifying the numerator, then you treat everything in the form of a over or z over w. So it is much better if we start by simplifying the numerator. We get 2 plus 2i minus i squared all over 4 minus 3i. This is going to be 2 minus I plus 1. Just because this is minus 1, minus 1 times negative is going to give us a 1. So over 4 minus 3i. So this is just going to be 3 minus I over 4 minus 3i. You said it. Since if we check here, this is what they got, right? They'll just get the same thing, 3 plus I, which is what we get here. Let me check. This is minus, yeah, it's plus I, this one, because it's 2 minus I, right? Then we're just going to get this. After getting this one, we're going to multiply here by the conjugate. The conjugate of the denominator is 4 plus 3i. 4 plus 3i. You see, right? And I remember I said that in the denominator it's better to say 4 squared plus, you take the one of a negative, minus 3 squared. You see, then 4 times 3 is, you're just going to multiply this like this. It's 12 plus 9i plus 4i plus 3i squared. Then this is just going to give us 12. This is I squared, so it's just going to be minus 3. 12 minus 3, then this is 4 plus 9, is going to be 13. I all over, this is 16 plus 9. Right? Then this is just going to be 25 in the denominator. The numerator is going to be, I think it's 9 plus 13i, if I calculated correctly, right? Then if we check, that's what we got. You're just going to put it in the form of a over b. You see, a plus bi. Just going to put it in that format of a plus bi. All right, like this. So now, if we check, it is not that difficult to work with such questions, right? If it is given to you like this, start by working the numerators. Start by always, if you're given to, it's given to you like this, zw over r. Start by working these ones of multiplication. Then you'll come and work this together. You see, right? To simplify things. Now, when we come to this one, so you can solve this in many ways, but it is much better to start by doing this. You know that I squared is also minus 1. You plug a minus 1 here. Minus, this is just I squared times I minus 2 over this I squared times I squared times I. We can even try to simplify it like this, right? If we check, this is minus 1 minus 1 I minus 2 over minus 1 I. It is simpler to simplify it like this. Then this will just be minus 1. This will give us positive I minus 2 over I. So it would be much better if we use this 2 to be 1, right? And then we just multiply with this I, then we subtract with the numerator. So it can be minus 1 plus I times I minus 2 all over I. Or if you want, you start by simplifying this one, but it's fine in this way, right? Then you can say this is equal to minus I plus I squared minus 2 all over I, which this is going to be equal to minus I minus 1 minus 2 all over I, and it's going to be equal to minus 1 minus 3 all over I. If you can check, I think this is what we are getting so far here, right? If you want, yeah, so I said that you can start by solving this one in this case, or you start by simplifying. If you can check the answer they got here, it's minus 1 plus 3i. If we continue there with the way that we did it, we're going to get the same solution, because now you're going to multiply by the conjugate here. You see, right? Then what do you think is the conjugate of this? You can tell me, what do you think is the conjugate of this? What will be the conjugate if we multiply by this? Didn't you guys see the conjugate when I was showing you somewhere here? I think you should have checked that. What is the conjugate of this here? How we multiply by this? Remember, the negative is going to be considered to be the one of the denominator, right? That's why they multiply by a positive one. So for us, it means that we're going to say this. We're going to say this negative, which this one is for a numerator, that one. So since we don't have a negative here, it means that our conjugate will be a negative I. Even though we're approaching this the different way, we're still going to get the same solution, right? So this is going to be negative I times 1, positive I, and then plus this will be 3i all over minus I squared. And negative I squared will be positive. This is 1. This one was I. This is no. Let me do this. I mistakenly used that one as 1. So I'm just gonna say this is negative I positive I squared, negative times negative, positive 3i all over negative I squared. And this is going to be, this negative I, it's gonna be negative 1 plus 3i, and this is negative 1, no, it's negative, and then this is negative 1. That will give us a positive 1, negative 1 plus 3i. You see, right? So you can decide which method to use, right? You can start by simplifying this one, or you start by multiplying them like this. At the end, you'll get the same solution. Minus 1 plus 3i, right? Which is this. I'm sure we see this, right? Now, we have checked that, we've seen that, oh, the answer is the same. So let's look at the next possible example that we can be presented with. Now they say solve for x and y in the following expression. So your aim, guys, the way for you to write this or to solve this, it's for you to say, I'm going to express the left hand side as in the form of a plus bi, also express the right hand side in the form of x plus bi. The reason why you're doing this, because you can equate these, the ones which are more like of a like term. You see, right? So it means that when we are going to solve this one, we know it's 3x minus 3iy, which is equal to 5 minus 9i. Already, the real part here is that 3x is equals to 5, meaning that x will be equals to 5 over 3. You see, right? And also the imaginary part is that minus 3iy is equals to minus 9i. The i's will cancel when we divide. We're left with minus 3 equals to minus 9. Then this is like 3y is equals to 9, and then y is equals to 3. You see, right? So if you wanted, we would have started here, which is where also they would start, right? After equating them like this, then they start here to say that y is equals to 3 and x is equals to 5 over 3. I'm sure we see this, right? Now, again, we're going to do the same thing for b. We're going to express the left hand side in the form of a plus bi. We express the right hand side in the form of a plus bi. Yes, right. This is just going to be 3x minus 6iy minus 2x minus or plus 2iy, which is equal to 7 minus 16i. And this is going to be 3x minus 2. This is x. This is minus 4iy. This is equal to 7 minus 16i. So it shows that x is equal to 7 and minus 4y is equal to minus 16, meaning that y is equal to 4. You see, right? So we're just going to express the left and the right hand side in the form of a plus b. We say that x is equal to, how did they get 8 here? Let's see why they got 8. Negative, but didn't I write positive there? Unless if they copied negative 2. Oh yeah, mistakenly the sign here, which is going to be 8 positive 8, which this gives us minus 2. Yeah, it's fine. So we see that this is what we'll be getting, right, if we do our computations correctly, right? Our x and y. So those will be our real parts. Now when we come to this one of c, with c it's going to be like this. Let's check what we have. We have a root with c. With c we're just going to start by squaring both sides. We're going to say that minus 3i squared is equals to x plus I. Already the right hand side is fine. We want to express everything in the left hand side in the form of a plus bi. Alright, and then we're going to simplify the left hand side. We get this, and then this was going to be 9 minus negative 1 minus 6i, which is equal to x plus iy, and this is like 10 minus 6i also x plus iy, meaning that x will be equal to 10 and y will be equal to minus 6. You see, right? Then we got 10 and minus 6, meaning that that's what we'll be getting. Isn't x 10? Let me see if they didn't it's minus, this is 3 minus 2, your minus 3 times, it's, let me say this, it's 3 squared first, plus 3 times minus I times 2 plus minus I squared. Then this is 9. This is minus 6I. This is plus I squared. What did the rate mean here? Let me see. If it was, oh yeah, I should have put this inside the brackets. Yeah, don't forget to put this inside the brackets, right? I'm writing so fast that sometimes I forget to put them inside brackets. So this would be 8, meaning that x would be 8, right? Like that. Now if we look at d, it's going to be also simpler in a way that we're going to express the left hand side in the form of a plus bi, and then we make sure that we equate it to the right hand side. Already the right hand side is fine. So this is going to be 6x plus 3iy minus 2y plus I 2x, which is equal to 10 minus 7i. And then this is going to be 6x. We group the real parts, right? Plus 3iy plus 12ix, which is equal to 10 minus 7i. So you're going to group them. So when you group them, you're going to have 6x minus 2y is equal to 10. You group the real parts, then you group the imaginary parts, also minus 7, right? And then if we check, we need to be able to manipulate the two. We can check the ones that can easily take us there. If we look at x, this one is in 12x, this 6x, meaning that I can easily multiply this one by a 2, and their signs are the same, right? I can multiply this one by a 2. I get 12x minus 4y, which is equal to 20. Then I take this, subtract this one, right? So it's going to be 12x minus 12x minus 4y minus 3y. It's like I take this, I first write it here, minus 12 minus 4y, right? Then I subtract this one. It's going to be minus 12 minus 3y, which is equal to 20 minus 7. You see, right? Now, if we check this, here we're going to get the 12x will cancel out, we'll get minus 7y, which is equal to this is 27. Then you can divide here and find your solution. Alright, meaning that your solution will be somewhere around here, right? Then after finding your y, you can go back to find your x. We know that 6x minus 2y is equal to 10. So you can easily come and say that this is 6x minus 2 minus 27 over 7, which is equal to 10. And this will be 6x plus what is going to be 27 times 2. Then you're going to solve your solution from here, right? Then let's see what would they get. So let's see, what was it? Oh, well, let's check. And then what they do, right, they simplify this, which is 6x 3yi minus 2y plus 2xi, which this is equal to this. Then this is 6x minus 2y 2x plus 3yi equals to 10 minus 7. And then which is what we got here. If we check, we also got the same thing. 2 times 3 is 6. Then it's 3iy, it's minus 2y, it's plus 2x ix. Let me check. Then this is this, and why did I get 12 here? Yeah, I'm really tired. This is 2x. Let me just fix this. This is 2x minus this, and then there's supposed to be 2x. If it's 2x, meaning that I should have multiplied this one. Yeah, let me fix this one because it's supposed to be 2x, right? I'm going to fix it from somewhere here since I had mistakenly copied a wrong value. Let's see what we're going to get. And then we had this equation, right? And also this equation. So I said that we're going to multiply this one by 2. So if we multiply this one by 2, we are going to get, let's see, 12. Oh, we can multiply this again because that one I thought it was 12, right? So we can multiply this one by 3 instead. so that we can have 6. So this is going to be 9y plus 6x, which is equal to minus 14. No, it's not minus 14. What is 3 times 21, right? Minus 21, yeah. Just confirm them using my head. Then 6 minus 6 will cancel out. Then minus 2 minus 9, we're going to get minus 11y, which is equal to 10 minus 21. Minus 21, it's like 10 minus 21. It's going to be like 10 equals to 10 plus 21, which is 31. Meaning that y is going to be 31 over negative 11. Yeah, then we would easily find our x here. So let's use this to find our x. Let's see. So if we try to solve, this was equals to 10. So you can try to solve for x here, right? Then let's see when they got, I think y is negative 31 over 11. If you plug that in to solve for x, you're going to get this. Just that I don't have a calculator here, right? So this is what you're going to be getting. So for now, I think that's where we're going to stop, right? Then the things which we're going to prove next would be, I think we've already done these ones of real imaginary form. And then let me check the things which we're gonna be doing. We're going to be doing yeah, we're just gonna, so what I would please with you now is that please do this tutorial so that when we meet, we're able to do the modulus argument. This one I want us to do it contact. I want to see people when I'm doing it with them, right? So that you can participate and so on. So if you can miss this part, you'll have a problem the entire topic, because this will be used everywhere until the last topic in complex numbers, right? So